Hello, Math 1050. This is section 4.3, talking about logarithmic functions. There are 5 topics in this section, starting just with your formula sheet really quick. So all this log stuff is on the back of the DSU formula sheet. So you have the sort of definition or the equivalence between log form and exponential form on the very top of the back of the formula sheet, and then you have the 5 log properties. So we'll be talking about some of these in this section. Some of them I think are in the next section though. Anyway, all that log stuff is on the back of the formula sheet. So the first topic is converting between logarithmic and exponential equations. So you're just supposed to rewrite the equation in the form requested. So the first one here is a log equation, and our goal is to rewrite it as an exponential equation. So you do, again, have this conversion on your formula sheet. So if you have log base b of x equals y, it's equivalent to b to the power y equals x. So our base in this log is 2, so the base of our exponential is going to be 2. The thing that the log is equal to becomes the power on the exponential. So this is going to be 2 to the power negative 5 is equal to 1 over 32. So this is what we would type in. This is the exponential form of that equation. Part B here is an exponential equation that we are going to rewrite in log form. So whatever the base of the exponential is, that's also going to be the base of the log. So this is going to be a log base 7. And then the part that the exponential is equal to is what goes as the argument of the log. So log base 7 of 49 is equal to the power 2. So whatever the power is on that exponential, that is what the log is equal to. Logs are equal to powers. Okay, so the next one is to evaluate logarithmic expressions. Now, the way that we're going to do this, and sometimes people get stuck on this topic because they just sort of can't remember how to do it, but we're going to evaluate these logarithmic expressions by thinking about their exponential form. So our goal is to say what this is equal to. So if we think about this in exponential form, it's saying 2 to what power gives me 1/4. So you can kind of see a 4, you can see that 4 here. So 2 squared is 4, but in my little equation that I wrote here, the 4 is in the denominator. So the power and the answer to our question is -2. The negative to move that 4 down to the denominator. So when you're doing this topic, kind of try to think about exponential form of the equation to help you come up with the answer. If your argument on your log is a fraction, most likely your power that you're looking for is a negative power. If you see an log log that does not have a little base written, it's a base 10 log. So this is 10 log base 10 of 1000. So if I think about that in exponential form, it's 10 to some power gives me 1000. So I think about what power of 10 is 1000, and so our answer here would be 3. All right, the next topic is to convert between a natural logarithm and an exponential equation. Now, you do have the log conversion on your formula sheet, but it doesn't have it separately written as base e. But if you have a log that is base e, we usually write that as a natural log. So you never really see that little base e there, even though it is base e. So if you want to convert between a natural log and an exponential, you kind of have to remember that that natural log is base e. But other than that, the conversion is exactly the same. It's just that the base isn't written there. So if I want to rewrite this exponential as a logarithmic equation, it would be a log base e of y is equal to 7. Except we don't usually write log base e, we usually write natural log. So that's the natural log of y is equal to 7. Just in general, sometimes people don't realize that that is a lowercase l, and this is an n, a lowercase n. Usually, I guess people figure out the n part, but I get a lot of like people who think that this is an I. It's not an I, it's an L for log natural. ln, log natural. Okay, so this next one is a natural log of x is equal to 8. So that's base e, because natural log is always base e. So in exponential form, this would be e to the 8th power equals x. And again, you can refer to the little conversion formula on your reference sheet to do these conversions. Just remember that natural log is base e. Okay, this topic is about graphing logarithmic functions. So you have to graph the function and give the domain and range. So a logarithmic function has this shape. The exact curvature depends on the base of the log. So this one is a base, this first one is base e, and the second one is base 2. Log functions have a vertical asymptote. They do not have a horizontal asymptote. So you can see the vertical asymptote on these two functions. So one here, I guess they're both at 0 here. Even though sometimes, especially with a higher base, it can start looking like this is getting flat over here, it's not. Logs do not flatten out on this side there. They just get, higher and higher, but they grow very, very slowly. So they do kind of sometimes look like they're getting flat, but they don't. So only one asymptote, and it's a vertical asymptote. Transformations of log functions work the same as usual. They can shift left and right, up and down. They can get stretched. But with logs, we usually try to focus on, I guess, one key point or like 2 key points. So that's the way I'm going to show you, especially with Alex, because it will be your job to plot the asymptote and 2 points, and then you can push on the graph button and it will draw the picture. In the domain for a log, because of that vertical asymptote, is going to be limited. So like the domain of this one would be from 0 to infinity. But the range for a log graph is all real numbers. Like I said, it's not going up very quickly, but it does keep going up. So eventually, not very fast, but eventually it will, take on all those different y values. Okay, so the way that we're going to be graphing these again is to plot the vertical asymptote and to find 2 key points. So the vertical asymptote, you're going to set the argument equal to 0. The argument is like the stuff inside the log. So like if it says log base 2 of x plus 7, this is called the argument of the log. So we're going to set our argument equal to 0 to find the vertical asymptote. And then when we find our 2 key points, we're going to set the argument equal to 1, and we're going to set the argument equal to the base of the log. And the reason we do that is because log base 1 of 0 and log base b of b is 1. So if we can figure out what x values make the argument 1 and which x value makes the argument b, that gives us some, nice integer points on our graph. Okay, so our first function is g of x equals log base 3 of x plus 4 minus 1. So the vertical asymptote is going to be the argument is equal to 0. So if I want to solve that, I would just subtract 4. So my vertical asymptote is x equals negative 4. So we could plot that over here. Okay, so to find 2 points on the graph, for this function, the argument is x plus 4 and the base is 3. So I think about what x value is going to make the argument 1. Well, if x plus 4 is equal to 1, then our x value that we're going to focus on is negative 3. And again, I'm choosing that because if I sub negative 3 into the function, it looks like log base 3 of, and if I sub in that negative 3, it's a negative 3 plus 4, which is a 1, and then subtract 1. So log base 3 of 1 is 0. That's on your log property sheet. Log base any base, just log base b of 1 is always 0. Again, with exponential form, it's maybe easier to see. It's because b to the 0 power gives you 1. So our first point, this is 0 minus 1. So our first point is negative 3, 1. Sorry, negative 3, negative 1. Our next point, our x value that we want to focus on is the x value that makes the argument equal to 3, which is the base of the function. So if we want to think about when does x plus 4 equal 3, well, if we subtract the 4, we get x is equal to negative 1. Now, the reason we chose that is because when we sub in negative 1 to our function right here for x, this becomes log base 3 of 3, subtract 1. Again, these subtract ones at the end are just part of our function at the top there. So log base 3 of 3 is equal to 1. So this is 1 minus 1, which is 0. And again, for any base, that's true. Log base b of the base is always 1. It's easy to see in exponential form because we know that b to the 1 power is b. Okay, so our second point is negative 1, 0. And then in ALEKS, once you have 2 points and the asymptote graphed, ALEKS, you can click on the button and it will sketch your log graph. So our domain here is from the asymptote over. The asymptote is not included, so it's a parenthesis from negative 4 to infinity. The range of these is all real numbers. They do not flatten on the top. They continue to grow, they just grow very slowly. Because these graphs are a little bit tricky, we are going to do a couple together. So for this log, for this function, it's 2 minus log base 4 of x minus 1. The argument is x minus 1. So our asymptote is x is equal to positive 1. All right, so now we're going to think about our 2 key points. Well, the argument is equal to 1 if x is 2. So we're choosing 2 as our x value. So then if we sub in 2 for x, it's 2 minus log base 4 of 1. Well, log base 4 of 1 is 0, so this is 2 minus 0. So that's the point, 2, 2. The base of this log is 4, so I need to think about what x value is going to give me my argument equivalent to the base 4. So that's going to give me an x value of 5 if I add that 1. So again, we chose that because this function, when I sub in 5, is 2 minus log base 4 of 4. The log base 4 of 4 is 1, so this is 2 minus 1, which is 1. Right there. So if we clicked on our graph button in ALEKS, it would sketch a graph something like this. So this log you might have noticed is different than the last one. The last one sort of went up and over. This one is coming down and over. And that is correct. It's because this log has been reflected with that negative sign there. So it is that shape because of the reflection. So the domain is still from the asymptote to infinity, and the range is still negative infinity to positive infinity. Always do your ranges from the bottom to the top. So you're thinking about what is the lowest value. Well, it eventually will get down, as far as you want it to go. It doesn't get there very quickly, but so it's easier to see that the top is going to be an infinity. But it is from negative infinity to positive infinity. There is no horizontal asymptote there. Okay, last one. It's log base 2 of x minus 2. Now, be careful here. The argument does not include that minus 2. The argument is just the x. In order for the x minus 2 to be the argument, you would have to see parentheses around the x minus 2. And since those parentheses are not there, it's understood that just the x is the argument. So vertical asymptote is from argument equals 0. In this case, our argument is x, so the vertical asymptote is here at 0. The argument is x, and the base is 2. So we first want our argument equal to 1, so that means our x value is 1. If we sub in 1, we get log base 2 of 1, subtract 2. Well, log base 2 of 1 is 0, so this is negative 2. Our base of our function is 2, so if we want the argument equal to 2, then that literally is the x value 2. So if we sub in 2, we get log base 2 of 2 minus 2, and this is a 1 minus 2, so that's a negative 1. So if we plot those 2 points, it's 1, negative 2, and 2, negative 1. So here's our function. The domain would be from 0 to infinity, and the range would be from negative infinity to positive infinity. So that's it for those graphs. Some of the times those graphs are a little bit tricky. Let me know if you have any questions or need any help. Thank you.